Hello, everybody. Hi. Yeah, so RIP the Frosted Tips. They had to go. My hair was falling down, so I'm pretty much a new person. Boo. Okay, yeah. Maybe I'll do it again. All right. Quickly before we get started, so today we're going to cover Gauss's Law. Quickly, one of the people in this class had just advertised this easy service hours. There's a high school science Olympiad going on. I think it's in the Union you actually do it. The information's up there, but so anyway, it would just be like administering it to some of the students taking it. I think you could rack up some service hours pretty easy. Just sit there, do your homework. So that is available going on this Saturday. Okay, some takeaways from last class. So last class, as I promised at the beginning, was very hard. Derivations are probably quite hard to follow, and that's to be expected. They're just derivations. However, there are some things I do want you to take away. One thing that we will use, again, pretty consistently is the formulas for charge density. For example, the formulas like lambda equals Q over L, or perhaps Q equals integral of lambda dx. Things of that nature, you'll see them again, not in super difficult ways, but you will see them again. Second is just the general idea of what we did last class. So if you remember, what we did is we chunked up these big objects into little pieces. We determined the electric field arrow coming from each little piece, and then we integrated over the whole object to get the total electric field coming from this irregular looking object. Okay, again, just the general idea. Following the derivations and recreating those derivations would be essentially an impossible task, so don't worry about that. However, the general idea is important of integrating little elements. There is on the next homework, this next week one due next Thursday, it's all on Gauss's law, but I put an extra credit problem of a simple example asking you to sort of recreate what we did last class. So it is on there as an extra credit. I would highly recommend doing it. The main takeaway from last class, though, is we derived some equations. I listed them at one of the first slides for the electric field near common objects: a disk, a ring, a plate, a long line, and a spherical shell. Knowing those formulas is the main thing you're going to want to take away. I did forget to mention, though, we did a spherical shell, like a hollow shell, and we found that outside, in a huge coincidence, you could still use the point charge formula of kq over r squared, and inside the field was 0. I did forget to mention that kq over r squared outside the shell, it also works if you have a charged ball rather than just a shell of charge, if it's filled in with charge the whole way. However, a word of caution, inside of a charged ball, the field is not 0. It's going to be something else. In fact, we're going to derive that next class using Gauss's law. Okay, and even those equations from last class, which were derived in a really hard way, you're going to see them again today because we're going to derive them in an easier way using Gauss's law. But something I do want to reiterate is we are just doing derivations. When I was TAing this class last semester, people were re-deriving the formulas every time they met a charged disk or every time they met a charged line. Once you have the formula for the electric field near the object, you never need to re-derive the formula. You can just plug in the numbers for the charge density of your line and how far away from your line you are. So once you have these formulas, that's going to be the main way you'll apply it. But these derivations are important to know, especially the ones from last class, but also the ones from this class. The general method of the derivation is highly applicable to other topics. Okay, and last thing is examples will return in droves. Not next class, maybe, there'll be a couple, but next class. These derivation-based topics are really hard to get examples in, which is part of the reason they're so hard to learn and teach. So don't worry, once we get to voltage, we're going to be back into the promised land of examples. Okay, so did I lose? Oh, okay, that's fine. Okay, so first question we're going to address, you don't know what Gauss's law is yet, but I'm going to tell you what it helps us do, what it helps us find. Okay, and the answer is Gauss's law helps us calculate the electric field near highly symmetric objects. Okay, Gauss's law is a recipe for computing the electric field strength near objects, specifically highly symmetrical ones. Okay, last class we addressed the ring isn't that symmetric, but let's say an infinitely long plate. It's a very simple object, and it took an awful lot of work to do the derivation. So the question is, there surely is an easier way, and this is going to be the easier way. Okay, but there are some good and bad things to doing the Gauss's law method compared to the method we did last time. I'll start with the bad. The bad is it only works near highly symmetric objects. A general object, even a ring, you cannot use this because they have to be symmetric. Okay, but there is good news at the same time. The first good news is that it's ridiculously easy. I'm going to underline ridiculously a couple times. The first time you do a problem, it might not be the easiest, but it will be ridiculously easy. And I realize I should be writing this a little bit bigger, but you know what that says. A question here?
What do you mean that a ring is not symmetric?
You'll see when we get to the example why you can't do it for a ring. A ring does look pretty symmetric, but we'll see why. Yeah. So the good news is it's ridiculously easy. His question, by the way, was you said a ring is not symmetric, and the response is it's sort of symmetric, but you'll see in a second why we can't use it. Okay, so the good news is it's ridiculously easy, and the other good news is these symmetric objects are everywhere. And even if your object is not symmetric, you can approximate it as one of these symmetric objects. Okay. Some notable examples we'll redo the spherical shell. It's one step. We'll do the line, which I didn't even do last class because it involved the trig substitution integral. That's also one step. The infinite plate is one step. The infinite, or a charged ball is two steps. So you'll see that these symmetric objects are pretty much everything you could be interested in except a disk and a ring. Okay, but we're going to have to take a quick sidetrack into something called electric flux before we can really use Gauss's law. Electric flux by itself, not too useful of a topic. It's mostly useful inside of Gauss's law. We will take this sidetrack, though, because it's good to know what it means. We'll also use magnetic flux later. That's more useful. So electric flux's definition is you're talking about the electric flux through a surface. It doesn't make sense if you don't specify a surface. The equation is pretty simple. You take the size of the surface, the area of the surface, and you multiply it by the strength of the electric field going through it. For example, if we have a 10 Newton per Coulomb electric field going through a 2 meter by 2 meter sheet, the total area is 4, the electric field is 10. So in this example, the flux would be 40 newtons meters squared per Coulomb. And I get the units by multiplying the units of electric field, which are newtons per Coulomb, by area, which is in meters squared. So Newton meter squared per Coulomb is a standard unit. Okay, but this is not quite it. If the electric field isn't perfectly perpendicular to the surface, you have to modify this formula to include an angle correction. So cosine theta gets tossed in there. Again, that means if the field is perfectly perpendicular, this factor goes away. But if it's not, you will have to include this factor. And I want to specify exactly which angle theta is. So theta is the angle between the electric field arrow and the surface perpendicular arrow. Some people refer to this as the normal to the surface. So in this example, the normal to the surface comes straight off the paper like that, right? You just draw the perpendicular thing shooting out of the surface. So the angle between E and the perpendicular is 0 because they point in the same direction. So the cosine goes away. It is a little bit wishy-washy if you go to 180 degrees because you have to define what is outwards from the surface. So I guess I will just specify the outwards surface perpendicular. But you'll see in practice when outwards and inwards matter. Okay, and if the electric field, let's say it were to poke in a different direction, like that way, the angle that you would use would be this angle right here, right? The angle between the electric field arrow and the surface perpendicular arrow. Everyone good there? I'll let you finish drawing the diagrams. Okay, I believe we have examples on the next slide. A question here? Yes.
Yeah, so it has to be perpendicular to the surface, right?
So it doesn't have to be perpendicular. What happens though is when it is perpendicular, the cosine factor is just 1. So it simplifies to just E times area.
Oh, I see. Once
Yeah.
it's 0, then
No, you're good. Excellent. Okay. And you're going to use that right now. Okay, so here are 2 examples of electric flux that I want you to do with ABCD cards. Let me know if you can't read anything on this. I kind of had to squeeze them in to get 2. Okay, top one is very similar to the one we just did. I tell you the value of the angle off to the side. Second one is a tiny bit harder, but you should still be able to do it. I should mention for the second one, you are adding up the fluxes. Hold on, let me. I need to mention this for the second problem. You don't add up the E arrows first. In that case, they would all cancel out. The instruction is you add up all the fluxes. If the flux is positive and the flux at another area is positive, you just add them together. So you're looking for the total flux. Okay. Who needs more time? Couple. All right. All right, I will forge ahead. Anyway, first question. Sorry, guys. Sorry if I'm bitchy. All right, first question. 3, 2, 1. Let's see. Okay, almost all D. I do see a couple C's. There's a reason I put this on there. The answer is D. There's a reason I wanted to put this problem onto the in class, okay? The reason is you guys are trained to, when you see a theta given in a problem, you instantly plug it in wherever you see a theta in the equation, okay? However, in the equation, the cosine theta, the theta is the angle between the E field arrow and the surface's perpendicular. So this is the value of the angle you need to plug into EA cosine theta. So the answer would be the E field 7 times the area 9 times cosine of 60 degrees. Just wanted to let everybody know about that. It's a common trick. I will try not to do it to you on like tests and stuff, but your engineering professors absolutely will trick you with it. Okay, second question. 3, 2, 1. Okay, I see a splattering here. Normally I'd have you fight with each other, but I'll explain it this time because it's kind of a little bit above your pay grade at this point. So the answer is C, which is, yeah, to celebrate. Okay. All right, the reason why the electric field at each point is always perpendicular to the surface. So there's no cosine theta involved anywhere. You just multiply E times area to get flux. Okay? So it's E everywhere times however much area it is occupying, and you're just adding all that up. So you just get E times the total area. And again, it's the surface area of a spherical shell, which is 4 pi r squared. And you just multiply it by the strength of the E field, which I told you to call E. Okay, so the answer is 4 pi r squared E. Again, this surface was really nice because the arrows were perpendicular to it everywhere. We're going to use this. I didn't pick this example out of nowhere. We're going to use this soon. Okay, so we're going to learn 2 forms of Gauss's law. The 2 kinds of problems you use it for are pretty disconnected from one another. They're obviously related because they're both Gauss's law, but it can be pretty tough to connect them, so I'm just going to treat it as 2 separate forms of Gauss's law. The first form of Gauss's law, and I'm not going to tell you where it comes from until the end of class, is that the electric flux through any surface at all, is equal to the charge enclosed by the surface divided by that weird constant epsilon 0 that I promised would come back. And again, the subscripts, I'll read it out for you guys. The subscript is Q subscript enclosed by the surface. And in formal equation form, you will see it written with this letter phi, maybe with a lowercase or with a subscript e. That stands for electric flux. So this is how you will see it in a textbook, but the above one is what it means. And again, this works through absolutely any surface you could possibly draw. A question? When we get to the point charge example, it might help you. So I'll wait until then, but ask me again if not. We'll use it later. Okay? So you can use this in one of two ways. If you are given the, okay, well, we'll do this way first. If you're given the electric flux going through a surface, all you have to do is multiply it by epsilon 0 to get the enclosed charge inside of that surface, which is pretty magical, considering you can do this for literally any surface you could possibly draw. The other way is if you're given the charge enclosed within a surface, you can compute the electric flux coming out of the surface. We're going to use that way second in some of our derivations. Just a quick remark here. Electric flux, when flux goes outwards, that is defined as being positive flux. And when it goes inwards into the core of a surface, for example, if it were going into the sphere, that is defined as being negative electric flux. And this flux here is the total with signs included. So for example, if you have flux going in and flux going out, you have to take the flux going out, subtract out however much flux is going in to get the net amount of flux going out. Sorry, I should say the net. I think I misspoke. Oops. I'm wondering if my, I think I am missing a slide here, so I'm just going to pop a new one in. Sorry for anyone who's using the PDF. I'm missing a slide here. This is one you're going to do on your discussion problems, but I want to show you how to do this. So let's pretend going into a box, I have an electric flux of 3 over epsilon naught going in and 1 over epsilon naught going out. And again, this is flux in standard units. I want you to find for me the net charge enclosed in the box. And this is going to be an ABCD card question. I just need to find the slide. I think it got moved. So yeah, you can get to that question here. Yeah. Sorry, the 3 is going in, and the 1 is going out. And you can also think to yourself, what sign of charge would create electric field arrows that look like this? All right, as soon as everyone has that, I'm going to go fish for the slide with the answers on it. I think it got knocked out of order. Oh, here we go. All right, 3, 2, 1. Let's see. B, B. All right, we got like 95% B's, some A's, and some C's. So I just want to quickly go over how you do this. Again, you'll see this on discussion. It's an easy test question. Wink, wink. It'll be on the practice test. Wink, wink. So you have 3 going in, and if you remember, flux going into a surface is defined as being negative flux. So you have negative 3 over epsilon naught going, or sorry, you have 3 over epsilon naught going into the surface and 1 over epsilon naught going out for an overall of 2 going into the surface. So the overall flux is minus 2 over epsilon naught. Again, the minus sign communicating the fact that it is going into the surface. And then Gauss's law says the flux through the surface is Q over epsilon naught, multiplied by epsilon naught on both sides to get Q equals negative 2. A question? Yes? Oh, epsilon. So just again, epsilon 0 is this funny numerical constant that sort of just appears out of nowhere. It has a value 8.85 times 10 to the negative 12th. And it can also be rewritten as K is 1 over 4 pi epsilon 0. It's just a number, though. OK, very good. And I just want to make another remark. This makes sense that it's a negative charge because you have more arrows going towards the charge or towards the box than going away from it. And that's vaguely what happens when you have a negative charge, right? Electric field points towards the negative charge. So that's how you can sort of guess that it's negative before doing the problem. Another question, yes?
So you just put the difference of the flux in?
Correct. I took the flux out minus the flux in the same way you would do forces right minus forces left to get the net flux. I just made the fluxes that way. Yeah. OK. All right, now we're at the main event. OK, so last time we used it in reverse. We used Gauss's law in a sort of weird way where I told you the flux going through a surface, and you used it to calculate the charge enclosed. Here, we're going to use it in reverse. We're going to use the known amount of charge enclosed within a region to compute the electric flux going through a surface. And then, since flux is E times area, we're going to divide through by area to get electric field. That's a rough sketch. You'll see how we do it in practice. So our goal is going to be to re-derive this formula that I pulled out of nowhere. Electric field near a point charge is KQ over R squared. I gave that to you, or I gave Coulomb's law to you out of nowhere. We're going to re-derive that formula using Gauss's law. OK, so here's our setup. We have some sort of I'm going to call it a positive point charge Q. And a general process for Gauss's law is the first step is to pick a smart surface. I'll tell you what defines a smart surface in a second. But you're going to draw some sort of surface around the charge in question. And the smart surface is going to have some properties that make it better than other surfaces. So to sketch a smart surface, you're first going to want to sketch what the electric field looks like near the object. Just a quick sketch. You don't need to put any numbers to it. And you do that just based off of the symmetry of the object. So for a single point charge, you know the electric field arrows point away from it. And again, that's just from, you don't know the equation of electric field near a charge. You just look at the charge and guess based off of the symmetry what direction the electric field arrows point. OK, now we're going to want to draw a surface. And the rules for drawing a smart surface are you pick one where the electric field arrows are perpendicular at every point. I should say the electric field arrows are perpendicular to the surface that you're about to draw. There's a little caveat for the infinite line, which we'll do in a second. It in some cases, you can allow it to be parallel too, but I'll show you that. So you pick a surface where the electric field arrows are perpendicular to the surface everywhere. And you also pick a surface where the E field has the same size everywhere. And although we don't know the size of the electric field, we're going to call it a variable E, and we'll find the value of what number E is later, or what formula E is later. So given that, what surface, using the example from before, what surface might be a smart one to draw in 3D around a point charge? Yeah, like a spherical shell. Okay, so our Gaussian surface, as it's called, is going to be a spherical shell around the charge. And I'm going to put the surface at a variable radius r. Okay? I'm not going to put it at a certain amount of meters away from the charge. I'm just going to put it at some variable r distance away. Okay, everybody done writing? Okay, I'm going to move next slide. So I see people are still writing. I'll let you guys. These are important steps. Okay. So I'm going to recopy down our diagram here. We have a point charge. We've drawn our spherical shell. The shell is a distance little r, which is a variable for now, but that's okay, away from the center. And we don't know how big the electric field is. We know it's the same size everywhere on the shell, but we don't know exactly what number it is, so we're just going to call it E for now. Okay, now we're going to use Gauss's law. So Gauss's law says the flux through any surface, so I'm just going to write E times A because there's no cosine here because the arrows are perpendicular everywhere. And it tells us that it's equal to the charge enclosed inside of the surface. I should say our charges of size q over epsilon 0. Okay, you already computed electric flux inside of or through this spherical shell, right? It was just the electric field size times the area, which was E times 4 pi r squared, right? That was what you computed in the example as the electric flux, because flux and E times A are the same thing when E is perpendicular to the surface. Okay, what's the charge enclosed by this surface? Little q. There's only one charge in the picture, it's little q. Okay, so here I've just rewritten Gauss's law. There's still some variables inside, little r, little e, or capital E. All right, but that's okay. Here's my equation. Now, and you're going to do this every time, I'm going to divide over to get E by itself. Okay, and what does this equation say? I'm going to group the 4 pi with the epsilon 0. It tells me the size of the electric field arrow anywhere a distance r away from a point charge is kq over r squared. Yes. So, yes, question. Again, epsilon 0 is just a numerical constant, like how g equals 9.8. Epsilon 0 is 8.85 times 10 to the negative 12. Another question, yes. So R came from the fact that when you're computing the electric flux through a surface at a distance, when you're computing the flux through a surface, you multiply the electric field times the area of the surface that you're considering. And I put this surface at some general distance r away from the charge. Right? I just put the surface at some distance r, and I didn't tell you what r was. It's a variable. Okay. All right, so here, we just re-derived in basically one step, maybe two steps, E equals kq over r squared for a point charge. That's pretty magical. Okay, let's do it for a couple other examples here. Okay, a spherical shell of total charge q. So this is a hollow shell. This is not my Gaussian surface. Maybe I should draw it. I'll draw my Gaussian surface in blue later. There's a total charge of q spread out around this shell. What might be a good Gaussian surface to draw, knowing that the electric field produced by this, just by symmetry reasons, looks like this? Again, it turns out it's another spherical shell is going to be our imaginary Gaussian surface that we're going to draw. Okay. Again, I drew this surface because the electric field is perpendicular everywhere and the same size everywhere along it, which I just sort of visually guess from the problem. Okay, and again, I'm going to put this a variable distance r from the center of the ball. It has to be from the center, that way the electric field is nice and symmetric everywhere along it. Okay, now again, Gauss's law, we're going to apply it to this blue surface. Okay, the flux enclosed by this surface, again, we don't know how big the electric field is, but we're going to call it this variable E. E is perpendicular to the surface everywhere, so the flux is just E times A. By the way, it's pretty safe to start Gauss's law from this step. You don't need to write the phi each time. Okay, the area of the spherical shell is just like before, 4 pi r squared, where r, little r is that variable. And the charge enclosed within that surface is just however much charge is on the shell. Exact same result we had for the point charge. Right? If I divide over by 4 pi r squared, we reach the exact same result for the point charge. Okay, and again, this only works outside the spherical shell because otherwise the surface encloses zero charge. If you take the surface within the hollow shell, there's no charge inside. A question, I'm going to have to move a little faster, but yes.
All right, so I get all the derivations and calculations. Could you explain what a flux is again?
So a flux for now is just some random tool. It's electric field times area. And that's good enough. That's good for now, yeah. Okay. Now, if you shrink the shell inside of the sphere, everything stays the same except charge enclosed is 0. You can divide through by 4 pi r squared if you want, but it still tells you that E equals 0 inside. Okay. Next derivation. The horrible line. Let me see if I can punch through it. Is it quick? Yeah.
So inside the shell or inside the object?
Only inside of a spherical shell. It's only good inside of a spherical shell. I'll actually go back and write that. Question near the back row?
Yeah, the sphere that you shrunk, was that like the blue?
Yes, it was he was asking which sphere did I shrink? I was shrinking the Gaussian surface so it was inside. The left-hand derivation only worked for R bigger than the shell itself. Yes. Okay, an infinite line with charge density lambda. This is an important example. It's still pretty simple, but there's a couple like new things that come up, so I wanted to give it. Lambda. Okay, step 1, sketch the electric field near the line. If you look down the tube of the line, it sort of spikes outward from the line. Okay, what might be a good surface to draw that has these arrows as perpendiculars? Yeah, a cylinder. And as you'll see, you don't have to be very good at guessing surfaces. The answer is always a cylinder, a sphere, and potentially a box. We might get to that today. So we're going to draw as our Gaussian surface a cylinder. Okay? One new thing, I'm going to give the cylinder a length L. L will cancel out later in the algebra, but I'm just going to call it of length L for now. That's sort of a step that you just have to believe in, and it will cancel out later. The other thing I want to bring up is technically this cylinder has area on the ends. Or even worse, the electric field is not perpendicular to that area. It's parallel to that area, which seems to violate our rules of what makes a surface smart. But it turns out that's actually okay, because all we need is that, and again, this is a little hairy, so don't worry if you don't completely get it. You can just understand the answer. It's going to turn out we just won't consider this area at all when we're doing E times A equals Q enclosed over epsilon 0. The reason is the flux of this arrow through this surface is 0 because it is at an angle of 90 degrees relative to the surface perpendicular. If it were punching straight through the surface, it would have maximum flux, but it's perfectly parallel to the surface. It contributes 0 flux. So the total flux going through the surface is only going to include this surface in black right here. It's not going to include the edges because there's 0 flux coming from the two edges. Okay, does anybody remember the formula for the surface area of that black region? It's 2 pi r, so the circumference of the cylinder. I should have mentioned I drew the cylinder a variable distance r away from the center, times the length of the cylinder. So it's 2 pi r L. Okay, and our formula says this is equal to the charge enclosed in the cylinder. Okay, now I have lambda, and I know how long the cylinder is. So the total charge enclosed, you can just use this formula, Q equals lambda times L, to get charge enclosed. Oops. Okay, here's my formula. E times A equals Q enclosed by my surface that I drew. over epsilon 0. Let people finish writing a little bit. Okay, as promised, the L's divide out. I'm going to move the 2 pi r over. Here's your formula for the size of an electric field arrow a distance of little r away from the line. In, again, effectively 1.5 steps. No trig substitution integral, no pain. I'll let you guys finish copying this. Okay, hold on. All right. A quick question, and this is something that I haven't told you guys yet in this class, is I gave you Coulomb's law and said this comes from somewhere magical, and I gave you Gauss's law and said it comes from somewhere magical. So where do they come from? So they come from something called Maxwell's equations, which tell you how the electric field and magnetic field must look near different kinds of objects. Furthermore, it tells you how they react when you change the electric field or magnetic field or charges around them. They're technically stated as derivative statements, such as divergences and curls. We won't be using those. But if you use some vector calc identities, they'll convert into integral statements. And that's the one that we'll be using in this class. This is a hidden way to say flux. Okay, next class we'll do the pillbox, which is for the infinite plane. And then we'll also treat some more examples. Yes, sorry, I had to get to the infinite line. Go on.
So those equations, do we need to like memorize them?
Absolutely not. No, no.
I just need to know that these equations came from both.
Yeah, A, I'm giving you an equation sheet with everything you need on the exam, plus you can take a cheat sheet on top of that. B, these are impossible to remember, and they'll be written on the equation sheet anyway.
Could I just get a quick definition for vacuum permittivity? I'm just kind of curious.
So it's a little bit of a wishy-washy definition. So on one hand, it's just a constant number everywhere you see it in equations. Why it's called the vacuum permittivity is you see where it appears in all Maxwell's equations, it appears here. It tells you how much electric field is created by a given amount of charge. It's a proportionality constant that was measured, saying if I put 1 coulomb of charge here, how strong of an electric field divergence does it create? People measured that, and then they assigned the value of epsilon 0. So in that sense, it's the permittivity, like how much space lets charge create fields.
Okay, thank you.
Yes?
I wasn't able to make class Friday, so I've been looking at the notes Friday, and I don't quite understand what an electric field is. Is it a force? What is it?
So you can view it, it's something that creates a force. Like Coulomb's law, we learned that 2